Good day, my name is Roelofs. I am one of the students at Maastricht University, and this is a machine learning club presentation about real-time frame upsampling, a paper recently published by Facebook. Just to touch on what real-time frame upsampling essentially means is in some way or another, you're playing a game, you take some low resolution or some bad looking frame, you put it through an artificial intelligence, and out comes the better frame, the objectively better frame, that hopefully takes less time to compute than the original one was at some very low loss of quality. So why is this needed? Why can't we just wait until our GPUs become better and can finally render 144 Hz 4K displays? Well, our GPUs right now, especially with some games, even the high-end ones, like the 1080 Ti's, the 20 and the 30 series from NVIDIA, are able to render most AAA games in around 1080p. That seems to be the limit in maybe 60, maybe 80 frames per second. And that was fine up until 10 years ago when the first 4K monitors started happening. And if you just go on Amazon right now, you can already see that we not only have the monitors that are 4K, but they also are 144 GHz, right? When comparing 1080p to 4K, you're talking about doing essentially 4 times more work to render each frame. 144 GHz means that instead of doing it maybe 30 or 60 times a second like you used to, you now want to do 144 times a second rendering. And well, the people want to use those things, and because people paid for them. However, you can still make the point that, okay, yeah, sure, we might just wait for 10, 20 years until the GPUs catch up. And you don't need to use the whole monitor, right? You pay for it, but you could play, excuse me, for 4K at 30 FPS, sure, playable. However, there's another growing issue, the issue of virtual reality. Because while you can accept some frame drops, some low performance from games on a normal monitor, in virtual reality, for example, here the Valve index, as you can see on the screen, requires a game to be rendered at 80 frames a second and 1540 by 1600 for each eye. So essentially you have two displays now. So you don't have one display of 1080p, now you have a high resolution display and you have two of them, and you need to display it at 160 frames a second. Well, that's pretty challenging. And the problem is that while in normal monitors, a frame drop could mean just some small loss in quality, when it comes to VR, any frame drops will result in nausea, seasickness, and stuff like that. It's a reason why there's a reason why the virtuality is run at least 80 frames per second. So in comes the main idea that the researchers had some 5 years ago. Let's take some low quality image, let's put it in some black box AI, and let's get a high quality and see what works and see how we can do that. Well, and the main two aspects that this research has focused on is improving the resolution of the image and improving and adding anti-aliasing to an otherwise aliased image. So the resolution speaks for itself. You just simply draw more pixels per square inch, per centimeter. However, with anti-aliasing, I'm going to just briefly go over what it is. So essentially, anti-aliasing comes into play when you have some very sharp contrast between two objects. Like in this case, you could see a branch and a sky, and the blocks in here are the individual pixels. You can see, for example, in here that in this particular pixel, there are 70% maybe black pixels and 30% blue. So this pixel to any objective viewer would be around, well, somewhere in the middle, somewhere maybe 3/4 between the black and the blue, right? So it would not be completely black or completely blue. However, that is very difficult when rendering an exponential game because you are sampling each pixel individually, right? And if you sample each pixel individually, you need to decide which position you sample the pixel. An aliased game is produced when you sample the middle of the pixel, and this is how the game starts to look, right? Because you could use a simple majority rule by sampling well, not majority. By sampling the middle, you basically look at the pixel in the middle, and then that's the pixel for the whole. That's the color for the whole pixel. And of course, if you look at the sky in such a game, you will see a branch not being a very smooth line. You will see it very blocky. People don't like that. People want to change that. So one of the ways to improve the performance is by sampling the each pixel more times, right? So you could sample every of the four corners and then take those values of the objects in there and then average them, right? So in this case, we would get 75% black, 25% blue, and we will just calculate some middle value about that. And well, that works well, good enough, but unfortunately, now to just make the image look not ugly, we were required to sample each pixel not once but 4 times, increasing the amount of work that we have to do linearly almost well 4 times. So people start looking at it like, hey, can we do it better? Can we do it? Can we do it with artificial intelligence? And out came three techniques: the DLSS from NVIDIA, the DLSS 2.0, and the neural supersampling from Facebook. One of the most important advantages of the Facebook paper is that it's public. We know how it's done, and it's platform independent, so it can work potentially on any computer, any virtual reality device, anything really. And as the authors claim, it's very easy to implement in the actual game engine, as the things that it requires on the game engine are readily available in most commercial products. And well, one other aspect of this paper is again that it's public, and it actually gives us kind of a look at how DLSS might work. DLSS is, of course, DLSS and DLSS2 is public, is completely private. The website does tell us some information on how it works, but essentially what they say is we take a low quality image, put it through a black box, and out comes the high quality, essentially. And we're gonna briefly touch on first DLSS, DLSS 2.0, what do they briefly do, and how are they distinguished from the neural supersampling proposed by Facebook. First of all, the DLSS 1.0 was game specific. You can see it as the developer taking, producing an early copy of the game, sending it out to NVIDIA. NVIDIA uses a supercomputer to play the game and record hours upon hours of extremely high quality footage. So just to give you an idea, instead of producing anti-aliasing with 4 pixels, right, with 4 samples per pixel, they would be using 64 samples per pixel to get even more accurate image. And then they would just feed it into the data and put the training parameters of the network into the new drivers. You would download the drivers, and then you could play the game using DLSS 1. Unfortunately, it only works for anti-aliasing, so you still need to render the frame at full resolution. And I have never used it, but I've read some reviews online, and people didn't like it. They actually preferred decreasing the texture quality or some other aspects of the graphics rather than enabling DLSS 1.0. DLSS 2.0 is a kind of revolution, though. It is claimed by NVIDIA to be game independent. We'll talk briefly about that shortly. It is faster than DLSS as DLSS 1.1, and it's supposed to be better. It not only does anti-aliasing, but also upscales the image. So you render at actually very low resolution, and you put it into artificial intelligence, out comes the high resolution, and it sometimes produces better frames than the target. Well, how can that be? Well, because something that we should understand is that the target that we actually want to reproduce is rendered on a supercomputer, right? It's an extremely high quality, as claimed by NVIDIA, not 4K, but 16K picture with extreme anti-aliasing. In that case, the target, the produced image by the artificial intelligence can in quality be between 4K and 16K, which makes it better than the target, essentially. I want to briefly touch on the game independent topic. So this is a claim made by NVIDIA in their promotional videos. However, when the games come out, I see time and time again both the developers and the company itself, NVIDIA, urging the players to download the very latest game-ready drivers, which to me kind of seems it might be game independent, as in it only needs to be fine-tuned on a very little amount of game data. as opposed to completely working as a plug-and-play feature. Because the reason for them urging the players to get the latest drivers would be for them to send the parameters of that trained network to the actual users. Well, that's how it works, right? So the neural supersampling for real-time rendering, the paper by Facebook, it's first of all platform independent. The whole research is public, but it has quite a few limitations. And something of note is that it is fully game specific, and actually it's more room specific than it is game specific. What it means we'll talk about again later. Well, the main idea, the crux of this simulation, of this artificial intelligence, is to use an autoencoder. An autoencoder, of course, is something that takes maybe an image on the left side. It summarizes it down to just a few digits. Maybe you summarize a big picture to 100 digits. And then from this 100 digits, the autoencoder tries to reconstruct the image. With the main idea being that the autoencoder is bound to summarize the most important features of the image to be able to reconstruct it. We have the same idea, but instead of reconstructing the same exact image, our input is a low quality image and the output is a high quality image. Well, that's exactly how it works. However, well, that seems simple enough, but the main issue is the actual architecture of the network, and not only the architecture, but what kind of features are we going to put in, because we cannot put in just the color, the frame, because we might be missing some information that we could otherwise retrieve. And what the paper by Facebook, the neural supersampling, did is they used they have three requirements for any game engine. First, they need the color, then the depth map and the motion vectors. The color is, of course, can be run by any game engine because it's something that that is required for the player to see. But as claimed by the authors, the depth map and the motion vectors is something that any game engine can compute, any commercial one, and it's very easy to do so, right? So it's very fast. And the input that they give is not only one frame, but also the previous 4 frames that they input. So the current frame that needs to be upscaled, as well as the 4 previous frames that just happened. And how does it work? Well, the first step to what they're doing is they're doing feature extraction. So they take the first frame, as can be seen here. They take the color and the depth of the frame. So the color and the depth map. And then they put it into a very shallow network, a 3-layer CNN, and out come the 8 feature channels. These 8 feature channels are then combined with the original color and depth to form 12 feature channels. And why 12? Well, the 4 additional channels come from 3 channels from color and 1 channel of depth. And they do the exact same thing for to extract the frames from to extract the features from the other frames. And well, the color, the depth, well, is good enough, right? It could be just a grayscale image with some pixels being brighter if an object is closer to you. But for the color, they use what's called a YCBCR. You might be familiar with RGB color scheme, red, green, and blue. Well, that took a while. However, the YCBCR is a bit different. The YCBCR stands for Y, the luminescence of the image, essentially a grayscale version of it, the blue ratio of the image, and the red ratio of the image. So while these 2 pictures on the left are just completely obvious, right, the actual image and its grayscale version, these 2 pictures are somewhat misleading. I took them from Wikipedia, and something that should be noted is that those images, well, do not represent what the actual blue ratio looks like. It is just some color map way of doing it, right? Because there's no essential color. Like, it doesn't look like that. It could be as well just be visualized as a kind of gray image, and it was done just to show that those 2 are different. And YCBCR, well, how it should be viewed for the purposes of this presentation is as kind of the same thing as RGB, but different. It has its own benefits, maybe its own problems, but you get the exact same 3 channels, and then you can you can reconstruct the actual image to be viewed from it. And something very interesting that you will come up against if you read the paper is that the first frame that is getting feature extracted is using YCBCR color encoding. So it's being converted from RGB to YCBCR, while the rest of the frames use the RGB colors. And why is that? Well, that's not really a reason. The way that the authors have described is that they have done it with just using all of the RGB ones, and then they just experimented, tried to switch RGB with YCBCR, and they found that their reproduction rate improved by a little bit, right? By maybe 1%. And because the input of these two things is different, they not only have one 3-layer CNN, but they actually have two. One that is used for the first frame, and one that is being used for all the other frames, for all the other previous 4. So the previous 4 frames all use the same 3-layer CNN to extract features. Then those features, they are mapped to a higher resolution by using what's called the zero upsampling, right? So why is it needed, and how does zero upsampling works? Well, you can imagine that if we render a pixel at a lower resolution, we can with some confidence say that if we were to scale it up to a bigger picture, right, then we already know with 100% guarantee the value of that pixel, right? What we don't know is the pixels around it. This pixels that need to be filled, right? That's just where the main issues come from. So zero upsampling, different from other classic upsampling methods, it doesn't try to fill in those missing pixels based on the values of the pixels around them. No, it just simply fills in the black pixels, like the empty pixels, right? So we take some low resolution image here with just 4 pixels, and we upscale it by uniformly distributing the black pixels in between those. And how it works in practice? Well, if you take a low resolution image like here, if you upsample it to a high resolution, you can see that this pixels still remain, like you can map one pixel to the other, but everything in between them is just completely black. Those are pixels that we need to come up with. Then, well, the extracted features, the one that we did, are actually wrong. Why? Well, the motion vectors and depth map doesn't provide us perfect information. The first thing that the researchers reported is experiencing ghosting. That's when, for example, you take the letter A and you would swipe it very fast over the screen with a very low frame rate. Then what you would see is that around the A there would be still very brief images of A where it used to be, as opposed to where it is right now. So it's kind of a trailing image that follows the original object. And our features cannot actually approximate the changes in lighting, right? What does it mean? Well, it might know when an object is moving or what color it is, but of course it can't approximate what kind of lighting sources there are in the scene and how those lighting sources exactly interact with the exact pixels, right? That could be a problem. So they use another artificial intelligence network for feature reweighting. So they generate the features, the zero upsampled features, as we previously saw here, and then they reweight them by pulling them through a network and produce what's called a reweighting map. So a map that tells us how important each pixel is. Of course, well, that introduces a kind of a hyperparameter because we need to understand what does it actually mean for one pixel to be more important than the other. For example, right, so what if one pixel, can one pixel be 100 times more important than the other? Can it be 10 times? Can it be 1 time? Well, the researchers have just by trial and error found that, well, the hyperparameter that they have set was 10. So one pixel can be 10 times as important as the other. And so the importance lies between the 0 and 10. Right. That is, of course, also a hyperparameter that maybe needs to be tuned for each game. And final reconstruction is all the features that we've gathered. They are input into this reconstruction network you can see here. And well, as we saw in the beginning, it's just it is reminiscent of a classic autoencoder problem, where you have downsampling stages here, like max pooling stages here, and then upsampling stages on the other side. And you might be asking, okay, so why does this one actually contain 64 channels, this one 32, this one 64, 64, 128, and so on? Why is it not growing? Why is it not going down? Well, it's because some people have used this particular architecture in the past, and it was shown to work well. How they found it? Well, usually they found it by trial and error. There are some ways right now that are becoming a part of the machine learning intelligence, of the artificial intelligence, is actually trying to find those things automatically instead of just poking and seeing what sticks. But yeah, this one was just used probably in some other paper, and it was used by the researchers because it seemed to work well, and they applied it to their problem and it worked well. So there's not much more details that go into it. The loss function they used to train their actual model was twofold. First of all, they used the computational similarity, where they would calculate the structural similarity between the images. So how are they similar to each other? The other one is a perceptual one. And the perceptual similarity is a kind of artificial intelligence network that is trained to correlate its score between each pixels, how similar they are, according to what humans might think, right? Because it is not often the case that the similarity threshold, because it can be computed in a multitude of different ways, is heavily correlated with how humans would perceive it, right? So okay, yes. So while in some cases you would be able to see so in some cases well, there would be some correlation, but of course, for example, if you warp a picture a certain way, for humans, you could ask them and they will tell you that it's almost exactly the same picture, while the machines will almost tell you that there's nothing similar between pictures. And why is this important? Well, because we don't actually care about what the computer thinks. We care a lot more about what the person thinks, right? We need to make it from a human standpoint of view very similar. Yeah. And the dataset that they used for VR, well, they used the datasets of where the people were play testing different AI games, and they were recording their movement, their wherever. Then they identified the head positions of every user in the game, everyone who participated in the thing, and then they would position a camera at such random position and let it navigate from one random position to the next. Of course, the random position would not be completely random, but it would be a sample taken from the actual humans who were performing this feat and playing such a game. The results are actually quite nice. On the left here, you can see what the input was, a low resolution image. On the right side, you can see what it should be. And of course, their model produces extremely good results. Right? You can already there is some loss in quality. As for example here, the star is not complete. However, when we look at the original image, we just see that it's 2 pixels. I'd argue that not even a human would be able to just look at this picture and say, "Hey, this is a star." So it's actually quite good, right? It gets back a lot of the very important features, like we see here that the grid is solid and not breaking apart, and that that this weird pattern here is actually lines on what looks like to be an air conditioning unit, something like that. Doesn't really matter. Some more results, the air conditioning that we saw, some screwdriver maybe. Of course, a human would not be able to understand what this even is, even remotely, but machine learning is able to do that. And yeah, well, so how does it actually work, right? Because I want us to focus on that particular feature here, right? The particular star. How does the machine actually know that it's a star, right? Well, you could argue that it looked at the previous frames and somehow deduced that those pixels form a star, but I don't think that is quite accurate. The reason for why it is able to reconstruct the star so well is also one of its biggest limitations. You see, the model the game itself that is displayed here is a one-room game. So a player in VR is in one room. He can interact maybe with a robot, maybe just play some cassettes, throw some things, stuff like that. And so this model is room dependent, right? It is trained to be in that room. It is trained on the input of what humans are produced, and you could say that it kind of remembered how a frame should look like. Right, it remembered how these features should look like, and remember that those 2 pixels maybe at this regular position around these pixels is actually a star, right? That is something that it potentially could remember, and well, it also brings us to our problems that we will be discussed later. But first of all, the benefits. First of all, we significantly increased the frame rate. The researchers reported, I think, getting around 20 plus frames per second, which is good enough. There's of course little loss in quality. As you can see here, these two look almost the same. So do this two, this two, this two. It's platform independent, meaning that as long as your computer is strong enough, it doesn't matter what hardware you're using, you can run it on any VR device. And it's relatively fast to train because you only need maybe 100 videos what the researchers have used, which is of course not potentially that difficult to do, right? And it's per room basis. So, well, if your game only contains one room, well, then you just let a few people play in it for a couple hours, and then you have all your data that you would ever need. However, well, the relatively fast train again comes back to that room, and it's still not perfect because in cases where there's a very large as a very high level of information in some part of the image, it still fails. As you can see here, well, a human would never be able to understand what this actually is, right? It looks like some dirt on the whiteboard. But the network actually say, well, this is maybe some square root, and this is some infinity symbol, and some circle maybe. But of course, this is very far from the ground truth, where we have a square, a triangle, and what looks like an atom. So this brings us to the drawbacks, right? The DLSS 1 only improved the anti-aliasing, or actually added anti-aliasing to the game, and it was game specific. So you would train it for the whole game because game usually shares some styles, some textures, some whatever. However, this one is room specific. Imagine you have a game, a very simple one, where you have 5 rooms and the player has to do something with them, but he can just press on the button and teleport to them. Well, this thing will be just perfect for you. But of course, any game where you actually have to move through the open world, you would have a lot of trouble with it. And as claimed by the authors, the performance drops gradually outside of the training room or the training environment in case that it's an open world game and you move too far from the starting spot. It needs a lot of training data, of what a person can do with their head, right? Because you have 5 rooms. Well, you have to train basically 5 different models, right? For those rooms, so you increase your data 5-fold. Of course, another question is how do you actually switch between the different models? For example, let's say that you don't teleport between one room and another in your game, but the player gradually walks between them. Well, at what point does one model switch to the next? When does the user experience some kind of a flash? Some kind of thing that they didn't ask, like does he notice the transition, because that's not something that we want. And of course, what is actually because of course the developers have used the actual people playing the game, but could we somehow approximate where the people would be putting their head, and could we generate the data completely automatically? Those are the questions that need to be asked. Of course, when you compare it to DLSS 2, which, as claimed by NVIDIA, is supposed to be game independent, mostly, right? Then of course is not as good. But just the fact that what they're using, right, different color encodings, they're using different feature extraction methods, feature reweighting maps, they use motion vectors, color maps, and stuff like that, depth maps. already gives us an idea of how a DLSS 2 can look like, and maybe you will remake the DLSS 2 and earn a lot of money from NVIDIA because they need to keep their trade secret. And so this concludes our presentation. Hopefully you enjoyed it. You can find all of the references to the paper and all of the images, as well as our Instagram page in the description. And subscribe and like the video. I'm gonna see you next time, guys.